Okay, this is the first hour of Physics 1B for November 3rd. Tonight we're going to be doing some more problems involving the first law of thermodynamics. What we learned last time was that the first law of thermodynamics tells us a way to find the change in the internal energy of a system by finding the amount of heat that was put into the system minus the work done by the system on its environment. And that is the first law of thermodynamics. And we would like to use it to solve a problem, or a few problems. The first one is this one right here. After we're done with that, we're going to talk about different types of processes for gases, talk about heat capacities for an ideal gas, and talk about a particular process called an adiabatic process for an ideal gas. And this will allow us to start talking about the way that a diesel engine works, which will kind of fit pretty well with what's going to be coming up next week, which is heat engines. So let's get going. All right, so here's our first problem we want to look at. It says a cyclic process. Figure 19.12, which is here, which is a PV diagram, which again is pressure volume, for a cyclic process in which the initial and final states of some thermodynamic system are the same. The state of the system starts at point A, here, and then proceeds counterclockwise in the PV diagram to point B. So it goes along this path. I don't know if you can tell, but there's a little arrow. So it goes this way first, and then proceeds counterclockwise, okay, and then back to A. So then it goes from B back to A this way. So it goes this way, and then it goes back this way, eventually returning to A, which is what makes it cyclic. It says the total work is W equal to negative 500 joules. The first question is, why is the work negative? So take a moment and look at the diagram. Why is the work negative?
It's going counterclockwise. If that helps.
No, I don't think that's the answer. Point B is less than point A. That's also not the answer.
It's the area under A to B is less than the area from B to A.
Something like that. Okay, so to find the work done, we have to find the area under the curve. So the first path, the area under the curve is here, right?
Yes.
The second path, the area under the curve, is also including the region between, which is here. But because we're going from B to A, in that direction, you're going to get a negative area when you go from point B to point A. And you're going to get a positive area when you go from point A to point B. So the total work is going to be negative because the area under the second curve is bigger than the area under the first curve. And the area from B to A is negative because it's backwards. Okay? So that's why. Part B says to find the change in internal energy and the heat added during this process. So we want to find the change in internal energy, and we want to find the heat added. Can anyone tell me what's the change in internal energy going to be?
Wouldn't it be 0?
Why is it 0?
Because it starts from one position and it ends back into the
That's
same
right.
position.
So since it returns to the same point, the change in internal energy has to be 0. And that means that Q should be equal to the work, and we already found that the work was given to be equal to negative 500 joules, so that means that the heat added to the system is negative 500 joules, which actually means there's heat being pulled out of the system in this process. That's it. Really easy problem. Okay, any questions? Left a lot more room than I realized. Can move this up a little bit. So. Okay. Next problem. Another first law problem. We want to compare thermodynamic processes. So, The PV diagram of figure 19.13 shows a series of thermodynamic processes. In process AB, 150 joules of heat is added to the system. In process BD, 600 joules of heat is added to the system. Let's go ahead and draw that on the picture. So here's our process, A to B to D. It says going from A to B, 150 joules is added. So there's going to be 150 joules of heat added here. We'll say that's equal to QAB. And then from B to D, it says that 600 joules of heat is added. BD, 600 joules of heat is added. So we're going to say 600 joules is going to be equal to the heat added along BD. Part A says to find the internal energy change in the process AB. So we want to find the change in internal energy in the process AB. Part B says the internal energy change in the process ABD, and then C, the total heat added. So B is going to be the change in internal energy in ABD. And then part C, the total heat added in the process ACD. So QACD. Those are the three things that we want to find. Okay. Part A. We know the change in internal energy according to the first law of thermodynamics along the path A to B has to be equal to the heat added minus the work done, right? We know that the heat added is 150 joules. How do we calculate the work done along the path A to B? Or can anyone tell me what it's equal to?
It's going to be equal to 0.
It's 0. Why is that?
Because you can't really find the area underneath that straight line.
Yep, a straight line, so it's straight up and down, so there's no area. The volume didn't change, right? And in order for there to be work, remember that work is defined as the integral of pressure with respect to volume, right? And if volume doesn't change, that's like doing an integral from point A to point A, or volume A to volume A, where the volume just stays the same, so the integral is going to be 0. So that means the change in internal energy from point A to point B is equal to 150 joules. All right? We can do the exact same thing as we go from B to D. So here we're going to need the heat added from A to B to D minus the work done from A to B to D. But we already saw that the work done along process AB is 0. So we're only going to need to find the work done along the line BD from here to here. So let's do that. The total energy added is going to be 150 joules plus 600 joules because we're going from A to B to D. So we're going to have 750 joules here minus the work along BD. Now all we need to do is to figure out the area all the way to the x-axis under BD. And that's easy enough to do because it's going to be a line that has a height of 8 times 10 to the 4 Pascal and a width between these 2 points here. So we'll just write down that we have, which, by the way, when we can pull the pressure out of this equation, what we get is that the work is just equal to the pressure times the change in volume, right? So 750 joules minus the work is going to be equal to this pressure here, which is the height. So 8 times 10 to the 4 pascals, that's a 4. And we multiply that by the change in volume, so 5 minus 2. And then times 10 to the minus 3 meters cubed. And that's going to give us an answer. You're saying the total answer is 240 joules? Is that what you get? Let's see. 8 times 5 minus 2 is 24. 24 times 10 is 240. 750 minus 240 is going to be 510, I think, right? Does that look right? Any questions? Okay, let's erase some of the stuff that we wrote here. Okay, so next we want to find the heat added along the line A to C to D. And to do this, again, it's going to be equal to, well, now it's heat added we're finding, right? So now we need to rearrange our energy equation. So our energy equation says that, let's use a different color now, says that the change in internal energy should be equal to Q minus W, which means that Q should be equal to the change in internal energy plus W, right? So if I want to find the Q along line ACD, I just need to find the change in internal energy from ACD plus the work done. And from C to D, there's no work done because it's a straight line, so we just need the work done along the line AC. What's the change in internal energy along the path A to C to D going to be?
Would it be the same as ABD?
Yep, it's going to be 510 joules. It's going to be equal to the same thing here because this goes from A to D. This one goes from A to D, so change in internal energy should be the same. We're going to add to that the work from A to C, so that is going to be equal to the height here. We just need to find the area under this curve, so 3 times 10 to the 4 pascals. Okay, and that's a 4 at the top there. Multiplied by the height, or the difference here, 5 minus 2. Okay, so 510, 3 times 3 is 9, times 10 is 90, 510 plus 90 is 600 joules. So 2 different paths, ABD and ACD. Along path ABD, there was 750 joules of energy put into the system. And along path ACD, there was 600 joules. So these can be different, even though delta U is the same. And of course, the amount of work done by the system is different in both cases too. In this case, the work done by the system was equal to 240 joules. In this case down here, this work ended up being equal to 90 joules. Okay. So more heat goes in process ABD, right? 750 joules goes in, and we get 240 joules of work out. In the process ACD, you put in 600 joules, and you get out 90 joules of work. And then, yeah. So you might say that process ABD would be more efficient at producing usable work, right? It's more efficient, right? Because you put in 750 joules and you got out 240 joules, almost a third of the energy you put in came out as work, right? Whereas in ACD, you put in 600 joules and you only got 90 joules out, which is only about a sixth of the total amount of work that you put in, or the heat that you put into the system, right? Something to think about. We're going to be talking more about efficiency and stuff later, but can you all see how the process ABD is kind of more efficient at generating usable work?
Yes.
All right. Any questions at all before we move on? Okay, let's try this one out. Thermodynamics of boiling water. So we have 1 gram of water in a closed container becomes 1 centimeter cubed of water becomes 1,671 centimeters cubed of steam. So we have water, we put heat into it, so heat goes in, and as a result, all of this water gets converted into steam. So we have steam here, so this is water, this is steam. We know that the volume here, we'll call this, would be volume 1, is equal to 1 centimeter cubed, and volume 2 is equal to 1671 centimeters cubed. And it says the heat of vaporization at this pressure is this number. Compute A, the work done by the water when it vaporizes, and B, its increase in internal energy. Okay? So the work done by the water when it vaporizes, and its increase in internal energy. Okay? So for the first part, to find the work done, we can do the pressure times the change in volume, because the pressure is constant, and we definitely see a change in volume here. So we're going to write this as atmospheric pressure, 1.013 times 10 to the 5 pascals, multiplied by the change in volume, which will be the final volume, which was 1671 centimeters cubed, minus 1 centimeter cubed. And then we need to multiply by a conversion factor to convert this to meters cubed. So we need 1 meter is 100 centimeters, and we can cube that. And this will give us our answer. It's going to be something like a little bit, it's going to be like 170 or so, maybe? What do you get here? Can you all calculate that for me? $169. Okay, that was close. Okay. In part B, it says the work done by the water when okay, we did that, and it's increase in internal energy. Okay, increase in internal energy. We're always just going to use this equation here. So to find the Q now, because we have a process where the water converts from liquid to steam, we know that we can find the Q by using the mass of the water multiplied by the latent heat of vaporization for the water. And we're told that we have 1 gram of water right here. So we can say that the change in internal energy should be equal to the mass, m, which will be 0.001 kg, multiplied by the latent heat of vaporization, which is given as 2.256 times 10 to the 6th joules per kilogram. And then subtract from this the work that we calculated here, 169 joules. And that will give us our answer. Tell me what you get. Okay, so the increase in internal energy, 2,087 joules. A little more internal energy when it's in a gas form, which makes sense. The gas molecules have a lot more freedom to move around and can move faster. So there's a more internal energy, which is like more kinetic energy, basically. Alrighty. So what's next? I think we're done there. We now want to talk about different types of processes, okay? And I guess one thing to mention is a different version of the, if you have infinitesimal changes of state. So our equation the equation is change in internal energy of a system is equal to Q minus W, our first law equation. We're going to note that we can also write this if we have an infinitesimal change in internal energy, that would be caused by an infinitesimal amount of heat being added and an infinitesimal amount of work being done. So this is an equivalent version of the first law, where all we really do is we just change the delta to du and then say that we're putting tiny pieces of heat in here. So just something to consider. Oh, and for us, dW is very often just going to be pressure dV. So this will be another version of the equation that we're going to see we use a lot. All right, no specific changes or anything like that, just a heads up of where we're going. And next thing we want to do is talk about types of thermodynamic processes. Okay, these are kind of like 4 words you're going to have to memorize the meaning of, basically. It's not a lot to memorize. So the first type is adiabatic process. Adiabatic process. An adiabatic process is a process in which no heat enters or leaves the system. That means that Q is equal to 0, which means that delta U for an adiabatic process, again, adiabat means no heat, Q equal to 0, that's what you got to remember. Then delta U should be equal to negative W in this case. The only change in internal energy can occur when there is work done on the system. So adiabatic processes usually occur when the process occurs quickly So when the process is quick enough that there isn't any time for heat to actually enter the system before the changes occur. And examples of this would be some of the strokes of a internal combustion engine. It's like the intake stroke. I'll just put ICE to stand for internal combustion engine. So like in the engine of a car. I think the book has a picture of a with a cork is popped on a bottle of champagne. It mentions that that's an example of an adiabatic process because when the cork pops off, it happens so fast that there's no real time for heat to enter the bottle or anything like that, and the gas just expands really rapidly. Okay, so that's what we... The temperature rises as the air-fuel mixture in the cylinder is compressed. Yeah, that's one of the things that they talk about. All right. Okay, so next, let's use a different color. So again, when you see adiabatic in a problem, remember that means heat is equal to 0. That's the key thing. Okay, next is isoquark process. This is a process in which, this is the volume one, right? Yeah, this is a constant volume process. And when you have constant volume, then again something is going to be equal to 0. So if the volume doesn't change, what is going to be 0? Can anyone figure that out?
The work.
Yeah, now the work is going to be equal to 0 because, again, work is equal to basically the integral of PdV, and if the volume doesn't change, then this whole thing is going to be 0. So the work done is 0, which means now that the change in internal energy is just going to be equal to whatever heat actually comes in or out of the system. So if heat comes in, the internal energy will go up. If heat leaves, the internal energy will go down. And we basically saw examples of this in one of these problems we did here. Like the process A to B and the process D to C in this example were constant volume processes, and we saw that there was no work done. All right, let's do another one here. Third, we've got isothermal. You can probably guess what that one is. You might think it would be Q equal to 0, but it's actually going to be temperature doesn't change. So this is going to be temperature is constant, right? Yeah. Temperature is constant. And I think that for ideal gases, that's going to allow us to say that the Q is equal to W because delta U is going to be 0. So I'm going to jump ahead a little bit here to say that for ideal gases, U depends only on T. The internal energy depends only on temperature. So that means that if temperature is constant, the delta U would be equal to 0, which would mean that Q is equal to W. Now, you can't do this all the time, but I suspect the majority of problems you're going to see in this class are going to be involving ideal gases, so that U depends only on temperature, which means that if we do have an isothermal process, you can safely say that Q is equal to W. Okay?
What's an example of that when Q does not equal W?
When some of the energy goes into the internal energy of the system as opposed to directly into work.
Got you.
Okay. Fourth. Yeah, we saw an example of that just a second ago. I'll just show you. I mean, I know it's just a problem, and maybe you're looking for something more concrete. But like here, for example, where the first problem we did, Q is equal to W, right? Because it was a cyclic process. And then we did a process that did start and end at the same point, so Q and W are different from each other now.
Yeah. Okay. They.
No problem. For isothermal processes, I think this is one where I mean, I can think of an example of this. Boiling water on a stove is an example of this. So if you have water in on a stove and you're boiling the water, right? And you're constantly adding heat at the bottom. So heat comes in, right? And the temperature is always going to be equal to 100 degrees until you boil everything off. So that's an example of an isothermal process where the temperature of the water is constant. Okay, finally is the isobaric process. In an isobaric process, this is one in which the pressure is constant. So for this one, since we know that Q is equal to U minus, what am I doing? Delta U is equal to Q minus W. Now, since W, for pressure being constant, we can just replace the work done with pressure times the change in volume. And that's going to be what we have for this one. I think that's all there is. Yep. There we go. So we've got these different types of processes. And the next thing that we're going to do is we're gonna analyze one specific one of these, the adiabatic process for an ideal gas. Let's see, it's 6:58. We've only been going for 30 minutes. We're doing really well on time. But I think this latter section is gonna get a little more complex. So let's talk about heat capacities of an ideal gas. Okay, so we have talked before about two different types of heat capacity equations, okay? One of them was Q equal to M times C times delta T, right? This is like the so-called MCAT equation. And we also learned one that involved molar heat capacity, which was Q is equal to N times C times delta T. But what we're going to learn in this section is there are two different versions of this right here. We call this the molar heat capacity. Molar heat capacity. And it turns out that there are different versions of this depending on if the system is at constant pressure or at constant volume, okay? So there's two different versions. You're going to have one equation that is Q equal to N, number of moles, times CV, delta T. So then this is C sub V. I think this one we already discussed, is the molar heat capacity at constant volume. This is the one I believe that we learned early on was where we could say that for monatomic gases, I think this was on the equation sheet for the test, that CV was equal to like 3/2 R, right?
Yeah.
Okay. So that's molar heat capacity at constant volume. Constant volume, that's what the V stands for. The other version we have is N is equal to N times Cp, the molar heat capacity at constant pressure, times delta T. So again, C sub P is molar heat capacity at constant pressure, and they're different from each other. I'll show you here in a second. Where's mine? Here we go. All right. So here is a system here that talks about how we measure this. So measuring molar heat capacity of an ideal gas. A, constant volume. B, constant pressure. Now, the equations they're using here are looking a little different than the ones I chose to use, and that's because we can rewrite these in their kind of infinitesimal version. If I write dq is equal to ncv dt, then we can talk about infinitesimal changes, and likewise with this one here, we can write this one as dq is equal to ncp dt, and that's what they've used here. So constant volume, you have a container of fixed volume, right? You add heat dq, presumably an amount of heat that you can measure that you've added, and then you look at the change in temperature. The temperature goes from T to T plus dt, and then all you need to do is to relate the change in temperature to the heat that comes in, and as long as you know the number of moles of the gas, you can basically use this as a way to measure CV. To measure CP, you need to have a system where you have a piston. The piston is allowed to move, and it specifically says it's a container with a movable piston that applies a constant pressure. So the piston applies a constant pressure so that the gas will always push back and have the same pressure. And in order for this to work, the volume of the gas is going to have to increase. That allows the gas to do work on its environment. And again, you can find the value of CP by doing some measurements. Now, if we actually look at what these values are, you can see over here a list of all of the CVs, molar heat capacity at constant volume, of helium, argon, and some other gases here. You'll notice that for monatomic gases, you get this relationship, right? R is about 8. 1.5 times 8 is 12. So you get this, right? 12. For diatomic gases, if you don't remember this, you get that CV is 5 halves of R. So if you take 8 and you multiply by 5 and divide by 2, you get about 20. So you see there's 20 in here. But, oh, whoops. Okay, so next, if you compare those to CP, though, you'll find that CP is always bigger, right? So CP here is 20.78, and for helium, and it's 12.47, right? These are all bigger. But again, there's some patterns here. The next thing you can see is that if you look at the third column here, where they've basically taken CP minus CV, these all happen to be equal to approximately just R, right? Especially for the monatomic and diatomic gases. And we don't really spend as much time talking about these ones here, because I think that they're just a little more complicated in terms of these values. But regardless, you can see that it looks like CP minus CV is approximately equal to R, right? 8.31, 8.31, 8.32 has the same units too, joules per mole Kelvin, right? So we want to prove this. Maybe we can prove this, right? All right. Okay, so let's do that, and let's use some of the knowledge we have of different processes to do so, okay? So here's what we want to do. We want to prove the difference between the molar heat capacity at constant pressure and the molar heat capacity at constant volume is equal to 0, okay? And here's how we're going to do that. So, think about a constant volume process. What was the name for that? I don't remember. I think it's isochoric, right? Isochoric. An isochoric process, right? In an isochoric process, we said before that if the volume is constant, that means the delta U is equal to what?
The change in internal energy. Oh, Q, heat. There you go.
Delta U is the change in internal energy. If the volume is constant, then the work is 0. That means that delta U is equal to Q. Now, for this derivation, though, we're just going to write it as du is equal to dq. And then what we're going to do is we're going to say we know what dq is. So if we have a constant volume process, just like we saw, where we send heat in, but we have a fixed volume container, so dq comes in. The result is it's going to increase the internal energy of this, and we know the way it's going to respond. If we have some kind of gas in here, we know that dq is equal to the number of moles multiplied by the specific heat at constant volume and then multiplied by dt. So the cool thing here is this gives us a value for du. We're going to use this here in a second. Okay? So now let's think about the constant pressure process. This would be the isobaric process. For this one, we said that if the pressure is constant, then that basically means the work is basically just equal to PdV, right? That means that the change in internal energy, which is equal to dq minus PdV, and then we say, okay, it's a constant pressure process, so we can replace the dq right here with in Cp dt. And we can get dt into our equation as well if we think about the ideal gas law. The ideal gas law tells us that pressure times volume is equal to nRT, so we could write this as N times R times T divided by V. And if our system was undergoing an infinitesimal pressure change, if the system was undergoing an infinitesimal volume change, and as a result had an infinitesimal change in temperature. So I guess I should draw a picture for this one as well. Well, you know what? I'll just use the picture from above because we already have it, and I don't want to redraw it. Yeah, maybe it helps redraw it. Okay, so we've got a container, right? And the container has a movable piston. So here's our piston, it can move, right? We send heat into the system, all right? As a result, the piston is going to move up. It's going to move up to a new position. Like, let's say it moves up to some new position, like right here. So here's our new position for our piston. It has a subtle change in volume here. So this is going to be our change in volume right here. And the temperature is going to go to T plus dt, right? Then we can say that we can relate here's how we're going to write this. Let's write it like this so it's a little easier to understand. We can say that PdV should be equal to nR dt. That's what I want to say. So using the ideal gas law, we're just going to replace PdV with nR dt. It's kind of like a change of variables, effectively, right? And this is equal to the change in internal energy. So now the part about this, I found this really confusing the first time I taught this, but now having taught this like 4 times, this makes a lot of sense to me. So the final step, or the second to last step, is to say that for a constant volume process, we know that the change in internal energy, right, is the same thing as the heat that comes into the system. It's constant volume, so it does no work on its environment. That means that any energy you put into it effectively stays within the system. Okay? And any energy that happens to leave the system, right, will then directly reduce the internal energy. I wanted to mention that this system doesn't have to isolate all the heat inside of it, okay? It's just that when you add heat, the energy goes up. When the system loses heat, the energy goes down, right? It doesn't have to hold all its heat in. Okay, so here's the argument. Whatever the change in internal energy is in the constant volume process, it should be equal to the change in internal energy in the constant pressure process. And the reason why is what we said a couple lines ago, which is that, where did I write it down? Oh, here we go. For an ideal gas, U depends only on temperature. It only depends on temperature. So, if I have a system that undergoes a temperature change that we call dT, right? Let's say, and let's use numbers just to make this a little easier to understand. Suppose that in this process here, dT was equal to plus 2 degrees Celsius, okay? And then I choose a constant pressure process in which dT is also equal to positive 2 degrees Celsius, right? Then the claim would be that whatever du is up here should be the same as du down here. Because the internal energy of the ideal gas is only going to depend on its temperature. And so as long as the temperature change is the same, then the change in internal energy should be the same as well. So that allows us to replace du on the left-hand side of our constant pressure process with what we got for the constant volume process. Does that make sense? These du's should be the same. Assuming that it's the same type of process, right? Assuming that we go from, like, let's say 80 degrees Celsius up to 82 degrees Celsius in this process, and we also go from 80 degrees Celsius up to 82 degrees Celsius in this process. As long as we choose the exact same temperature difference, then we expect du to be the same. Okay? Again, this really bothered me the first time I was trying to teach this. I didn't really understand it, but it totally makes sense to me now. Anyone have any questions?
So different processes, but definitely when it's the same temperature difference, du is the same, basically.
Exactly. That's right. Yep. And this equation also effectively shows you the difference between a isochoric and an isobaric process, right? In the isochoric process, everything you need to know about du is contained in this equation right here, right? But for the isobaric process, you need this whole equation because the volume can change, and that's going to change the internal energy as well. When the volume changes, remember, that means that the system is doing work on its environment, and that's going to affect the change in internal energy of the system. If some of the internal energy of the system is doing work on its environment, you need to take that into account, right? So it can't just be this term. It also has to be this term. Because what's happening in the latter case is that you're sending energy into the system in the form of heat, right? Some of that energy goes into the internal energy increase, right? But some of it basically escapes the system in the sense that it will do work on its environment. And you have to include that part, right? Okay. Now, those of you that are paying close attention can probably tell that we can massively reduce this equation, right? Because every term has a dt. We can cancel all those out. And every term has an n, which we can cancel out as well. So we're left with just CV is equal to CP minus R, which if we rearrange it tells us that R is equal to the difference between CP and CV, and that's pretty handy. It's pretty handy. All right. Anyone have any questions? Okay. The next thing we're going to do is we're going to talk about the ratio of heat capacities because this can be pretty helpful for us from time to time. So ratios of heat capacities. So we are going to define gamma to be equal to the big one over the small one. Since CP is always bigger than CV, we'll write this as CP divided by CV. This is a ratio that is going to show up in some of the calculations that we're going to do. Okay, and we can do some things with it. So if we're talking about a monatomic gas, for example, okay, so for a monatomic ideal gas, we said before that we knew for this one that CV was equal to 3/2 R, right? Then we can use this equation here. We can rewrite it in the following way. We can write it as CV plus R is equal to CP. So that would mean that CP for a monatomic ideal gas should be equal to 3/2 R plus R, which should be equal to 5/2 R, right? So if CP is equal to 5/2, then we can write this as gamma is equal to the ratio of 5/2 divided by 3/2. So gamma is going to be equal to 5/3, which is approximately equal to 1.67. So that's going to be for a monatomic ideal gas. In certain problems you have, you're going to be given this quantity. Okay. For a diatomic ideal gas, Okay, just to remind you, monatomic gas is like helium and argon. Diatomic gas is like hydrogen, oxygen, not Q2, O2, N2, stuff like this. So, diatomic ideal gas, we said that CV was equal to 5 over 2R, which means that CP is going to be 5 halves plus R, right? We use this equation. So 5 halves plus R is going to be 5 halves plus 1, which would be 5 halves plus 2 halves, which is 7 halves. 7 over 2. And then gamma is going to be equal to 7 over 2 divided by 5 over 2, which is going to be equal to 7 over 5, which is equal to 1.4. Okay. What else can we do with this? One other thing that I know is going to come up in some of these problems here is that we can take this equation here, R, and say that R is equal to, from this equation here, we can change this to be CV times gamma is equal to CP. If we do that, we're going to get that R equal to CP, I'll put a line right here. If we do this and then replace CP with CV times gamma, we'll get R is equal to gamma times CP, CV minus CV. Could factor out the CV, so we get gamma minus 1 times CV is equal to R. So this is a pretty handy equation. It can also be written as R divided by gamma minus 1 is equal to CV. So this is something we might need at some point in one of these problems. Just putting it in there. It also tells us that the ratio of R divided by CV is equal to is equal to gamma minus 1. However you want to write it, just something that's going to be useful to us. And now I think we can do a problem. Does anyone have any questions before we move along? Okay, let's do this problem and then we'll take a break. It says, a typical dorm room or bedroom contains about 2,500 moles of air. Let's write that down, 2,500 moles. Find the change in internal energy, that's our question, of this much air when it is cooled from 35 degrees Celsius to 26 degrees Celsius at a constant pressure of 1 atmosphere. So we have a pressure that's equal to 1 atmosphere, right? And we know that it goes from a temperature, let's call it T1, equal to 35 degrees Celsius, down to a temperature, let's call it T2, that is 26 degrees Celsius, all right? And we know the pressure is constant. And it says treat the air as an ideal gas with gamma equal to 1.400. All right. We have to find change in internal energy, which we know is equal to Q minus W. Let me change the color here so that's distinct from the green we're using for the symbols. The volume's not changing, right?
No.
So we can say that, right? That means that the change in internal energy, so the work should be 0, and the change in internal energy should completely be given by Q, which should be equal to number of moles multiplied by specific heat at constant volume multiplied by change in temperature. Now, we could go and look up CV for air, but we don't have to do that because we were given that gamma was equal to 1.4, right? And from this equation here, we can use that to solve for CV, right? So then CV is equal to R divided by gamma minus 1. And we can even just plug this in right here for CV. So we'll have N R delta T divided by gamma minus 1 should be equal to the change in internal energy of the system. So that's going to be 2,500 moles times the gas constant multiplied by the change in temperature, which it looks like is -9 or Negative 11? Is that right? T2 minus T1? 26 minus 35?
Yeah.
26 to 36 would be 10, so another, yeah, so it's 11. All right, and then we have to divide that by gamma minus 1, which will be 1.4. He's saying it's negative 9. Yeah, 26 down to 36. Should I just put this in a calculator? 35 minus 26. What is that? 15. It sure looks like it's 9 to me. It's negative 9, isn't it?
Yeah, it's negative 9.
Okay. All right, negative 9. And then we just divide by gamma minus 1, so 1.4 minus 1. And that'll give us delta U. Can you all tell me what you get if you calculate this? $4.67. Times 10 to the 5. Okay. It's negative, though, isn't it? Yeah, it's negative. Cooled down, so it lost energy, right? The molecules are moving slower now. That's what that means, right? Okay, good place to take a break if there aren't any questions. Are there any questions?
The fact that there was no change in volume, we went ahead and instead of using the delta U equals Q, we went ahead and used the delta U equals MC sub V delta T. Is that right?
No, we did use delta U equal to Q. Q is equal to this. From here.
Oh, yeah. Okay.
Yep. Other questions? Let's take a break for 10 minutes. So break until 7:34.